adjacent. So I'm really glad to be able to talk to you today. So you'll see what I want to talk about in a second. But I'm a faculty here in LSI and also biochemistry. We're mostly just sort of experimental structural biologists. We use cryo-EM, and I'll kind of highlight that in a second. That's mostly what we do. But then I have this side project that's been growing, which is what this is. And I want to sort of get all of your feedback about how we either can connect or help or sort of move on from there. So the motivation is how did I get here, and what was the motivation of what I built? And I'll tell you about this cyber infrastructure project that I built, the motivation of how we built it, the architecture of it. Then I'll tell you about how it's being used today. And so it's, this is a good audience to hear what you think and also what we can do with it. And so, yeah, let's just jump in. So where I think we are in sort of structural biology modeling world is that we're at this amazing point where all this modeling software, structure prediction is super powerful. Everybody wants to use it and no one knows how to use it, right? That's just disconnect of super powerful. Everyone needs to use it, but they don't know how to run. They don't know Linux. They don't know how to run it. They don't know how to interpret it, but they know they need it because when it works, it can be really powerful for their research. And so I feel like it's this gap that where my project tries to fit in amongst other projects that try to help people with life science research. And so I'll now motivate why we also need this in cryo-EM. I'll talk about what cryo-EM, what electron microscopy is for a brief second here. So the analogy I really like to use now is that electron microscopes are telescopes to the microcosmos. So if you think about it, us to Jupiter, super far, that's the same distance of us to a protein. And I feel like that helps put it into context that proteins are really far away from us. We think we, can control them because we can pipette them, but they're distant, super far away from us. And to give you a sense of the scale, there's this awesome video someone made of zooming in 9 orders of magnitude from a grid. This is a macro scale grid. So this is about a few millimeters, all the way to one exposure that we'll take on an EM grid. Cool. So now they're just going to zoom in. So this is, again, this is a tweezer. You can be holding this grid. Eventually, we'll switch over. Now we're in electron microscopy imaging. And now we can keep zooming. These squares are about 60 microns. And so a cell is about this big, let's say, a human cell. We're zooming in. These little holes or windows that we'll put proteins into. And these are about a micron in size. And then eventually, we get to an exposure image, which is about hundreds of nanometers wide. And any given protein, is in the order of 10 to 20 nanometers. So even that video is still hard to appreciate how far away it is. That said, that's essentially the scale that we're going across in EM. Cool. Okay, and then just with this analogy, we have this problem of every image we take is of a protein, but they're radiation sensitive, so they're super noisy. So all of our data is really noisy. So we'll collect lots of images. So the problem we have is we need thousands of exposures per data set just to see what's happening, and then we analyze it. And so even in electron microscopy structural biology, we have super fancy microscopes, and we have really nice model building programs and density maps. But in between is a big mess. And our field has had this huge growth because it's so powerful for structure determination that even inside of a structural biology field, most people are not super comfortable with Linux and supercomputers. They like to use interfaces and things that extract away from the command line. But they are still in this group of people who need high performance computing because they will take a terabyte of data just as a pilot study, and they'll do that over and over again. And they'll have these piles of data, need access to high performance GPUs and CPUs, and that's where we came in with this project. And so this has been happening since cryo-EM has been around. And so 6 years ago, I thought, I've been kind of always helping people with cryo-EM related image analysis stuff. And when I was a postdoc at UC San Diego, hanging around the supercomputing center there was clearly these initiatives to bring people in to use high performance computing who typically don't usually do it. So don't want to use Linux, don't want to use command lines, we use a web interface. And so there's this whole field called science gateways, which people here appreciate, which is part of the iTaser Science Gateway, lots of other projects are science gateways. And so we thought we'd make a science gateway for cryo-EM, where the idea was we'll have a web server, we'll host it out of San Diego Supercomputing Center. People could submit jobs via the web server to the supercomputer without seeing command line. And so the big mission for us was, like, we are just structural biologists. We don't really care. We'll add any software that can run on Linux. We're not software developers or algorithm developers. We're just users, expert users. So we'll add any software that's helpful. The idea would be everyone gets some access up front. Everyone here gets some default amount of computing time when you just log in. The software would be anything that runs on Linux that also doesn't require a lot of like tweaking and interacting, because we're extracting everything into a website, and so it's not interactive. And I think an important part of this whole project is that there's like expert users designing and running it. And so if someone has a problem, like, I know all of the software that they're running, and I can help them both like how to run the software, but also how to interpret the data. And so I think that's like a unique angle, is that you're not just like, you ran the command wrong, specify this number of processors. It's like, wait, what are you doing? Like, oh, you shouldn't do that. You should try this. Like that feedback I think is really important, especially as structural biology is growing. So the big trick to this was, how do you ingest data? So we're not uploading text files, we're uploading like hundreds of thousands of image data. And so what we did is we integrated Globus, which is a data moving service, into the like fabric of the platform. And so if you haven't heard of Globus, so Globus is this essentially as fast as you can moving system that can move data around. And it can do it, essentially separate from a website. So there's a server we're already running that can move data around. And the idea is there are endpoints, and Globus will orchestrate movement from your endpoint to the supercomputer endpoint. And the actual moving of data is pretty easy. The setting it up can be tricky because there are firewalls that can get in the way here and all these problems. But the nice thing is that there are APIs that we can use underneath this, so that when a user moves data in, we can only show them the data that they should see. And so it lets us sort of move in any amount of data we want, like terabytes of data, as long as it can get transferred. And it's as good as your networking, which might not be good, but it's as good as your networking is. All the jobs we run are at the Expand supercomputer. It used to be called Comet. And it has a lot of CPUs, some GPUs, not a lot, but this is what we have, petabytes of storage. Definitely good enough. So we made this thing. It's being used for cryo-EM, kind of like fringe for a while. But then I'll show in a second the user base, but we really jumped into the structural prediction world when AlphaFold was released, because you want to run the full AlphaFold package. Where are you going to run that? You can't use the Colab notebooks, but we already are running a supercomputer. Let's just run AlphaFold over there. And so at this point, what we have are a bunch of different structural biology tools. It's sort of like Mike's toolbox of structural biology is what it feels like right now. We have cryo-EM jobs that are these software packages called Rely-On, but then we've added all these structure prediction things because we could run it. It felt like in the beginning, it's like, well, we should run it. If you really want to run the full AlphaFold, it should be run somewhere for free. And so we added that. And then that started driving a lot of users. So we added, multiple when they came out, and Colab fold, this IPG fold, Omega fold, ESM fold, like anything. Plus other model building software that we use for structural biology, plus some like 3D reconstruction stuff. It's mostly a mixture of what I think we should have, plus what users request. The key bit here of like what people are using it for are, we built it for this, which is like the input data are images in hard. It's like hard to work with, hard to deal with this, but it was sort of needed, and people still use it for this. But what's taken off is this bottom part here, which is sort of like things related to 3D reconstruction, filtering, structure modeling, and structural prediction. Because these are much lighter weight jobs. You can use a web browser to upload text files, 3D files. Whereas here you have to use this whole Globus thing, which required like activation energy. It's still straightforward, but it was like definitely a speed bump that people would just turn away from. So with this, this has been like a big part of what we're doing now. To give you a sense of what this looks like, just while we're talking about the project, from the beginning, we were like, we're not going to deal with any user authentication business. We're just going to use this thing called in common, which is like how you say, like when you authenticate with Google somewhere, we'll just take as long as someone authenticates you as an existing, we'll take you in. And so what this looks like is you get redirected via Globus, and you can authenticate with Google, Orchid, University, like whatever. So anyone can come in, but they're authenticated, and we're not managing passwords, which is what's nice. And you don't need to like have a data breach or anything. Authentication, and then what happens is when you upload your data, we can use Globus APIs and only expose the data that you've uploaded to you. And so that's nice. Then you can download data, upload data through this system. And so I can't tell in the future, because I'm highlighting this because maybe some of you here have some image projects that this would help with to have this data moving service built. Again, it's definitely being used, but it's not the biggest use case. And so users can upload and download, and yeah, it's fine. The interface is really basic, sort of bare bones as far as like what it looks like. You can run different tasks, you can clone tasks, you can upload different kinds of files and run things. It's fine. So where we are today, though, is that so we have like 5,000 users, and the way it's been going is so like this is like cumulative number of users, and you can see where like AlphaFold was released publicly, and then we've been on this like trajectory of a few thousand users every so often for a while. And what we're seeing is that most of those people are like cell biologists, virologists, like cardiovascular institutes. The questions that we get for help are crazy. They're in these some like plant pathology departments that they can't run AlphaFold correctly. And so I think there's this keeps growing, and I keep trying to advertise this project because I can see that it's super useful for like life science researchers, but it's hard to get to them. And so I've already heard of the whisper networks of like, oh, you have a big protein complex, you should go run it on COSMIC2, and people pass this information around. And so it's nice having this project running in the supercomputing center because we can run jobs that take up to 2 days, and also they're using GPUs that are actually real GPUs, unlike the collab GPUs that are much smaller. And so we can do bigger and bigger structure predictions, like up to 6,000 amino acids right now. So pretty good. What we're giving out is essentially GPU hours to anybody who shows up. And so we're giving away, everybody here gets like 60 GPU hours to start, and then we apply for more time and manage that for you. And so everybody here could upload jobs right now. I've used this in classes that I teach, where I have everybody go run AlphaFold jobs, interpret them, let's talk about them, because this is the future of using it. Where we are, so like the whole motivation was cryo-EM, but this is like the last 2 years is like everything is structure prediction, because it's the sweet spot of like easy to upload, easy to download, but requires like serious GPU time to run a job for 4 hours, 8 hours, which you wouldn't do on a collab notebook, which can take which would be annoying because it probably won't work. So this is where we are as far as like we have these tools. Most of them are structure prediction. And so where we are today, like the current issues we have are honestly like rich text editors are like the biggest problem we have, because we want people to upload FASTA files, which are plain text. And it's like in principle, we could clean it up for them. We try to help them, but it's still, that's the uploading text file problem. Part is a big problem. We're definitely bumping into queuing issues on Expanse, the supercomputer, where we're hitting like queue limits where they don't want us to be that many of the same user in the queue together. Just managing user allocations is definitely tricky to know how much to give out to people, and then helping people debug their input files. That said, I feel like having a science experts behind it helps them understand what's going on. So we're both teaching them and teaching about the process of the job, but also the like science of interpreting it. What I'm trying to work on is probably updating with a different grant, trying to update the interface to make it like copy and paste the FASTA files in or something. I don't know, try to help them with this part. So the things I want to talk about from everybody here is like, what can we connect with any of you here? Are there software that would help you all if we hosted it for you? I've been thinking a lot about, especially looking at the sort of different projects that have lots of software tools. Like for us, we have like 30 tools now. It's already getting a little overwhelming, and I feel like we probably should be switching it to being like, what do you want to do? Single particle cryo-EM, structure prediction. And they say structure prediction, and you're like, okay, if you're a novice, we're going to hand you the most basic thing, and then just don't let them have to choose the software exactly, but just choose what they want to do with it. That's what I'm thinking of, one version of this. It feels like with all the like prompt-based stuff in our life now with ChatGPT. It feels like this should be prompt-based of like, I want to do a structural prediction of this, this, and this, and it just runs. The thing I've been trying to figure out is like, what do we do with all the structural prediction data? And so it seems pretty valuable. It's a gray zone. I don't understand. Maybe you guys have thought about this with like, is it considered intellectual property? I think it is, because you had to choose who goes where. But it also feels like a resource that should be shared, because if you have a bunch of high confidence, complex predictions, that should probably be released eventually. And then I don't understand what the future should be as far as interfaces, because people have definitely gotten used to now like Jupyter Notebook things. So should this, if I were to re-envision this, should it be Jupyter Notebook based or not? The downside of Jupyter Notebooks is that you have to like be in the queue at the same time. It's hard to get it all lined up to be on the notebook and on your queuing time. And if it gets you in the middle of the night onto the node, it's not super helpful. And then, yeah, so do you have tools to add? I'm also trying to figure out how to get this to be paid for sustainably. You know, like having people pay for fast response times, more computing allocations. One idea that maybe people would be upset with is like, you can pay to keep your results secret for, and if you're not going to pay, then we're going to share your results after like 6 months. You know, things like that. I don't know. I think people might be offended by that. So anyway, that's all I want to talk about. I mostly just wanted to like be here, introduce myself, talk more now or offline later. Use this. If you want to use any software, go use it, share it, use it in classes, do whatever. So that's it. Thanks. Mm-hmm.
The actual allocation, you have a number, the gateway allocation for access.
Mm-hmm.
Okay, I mean, you should be able to keep that sustainable if you have a lot of users and one was asked for more, so that's like constant issue. When you get a query just for AlphaFold, you know just AlphaFold, do you check against the AlphaFold database first?
Not yet. So yeah, we're definitely, there's like all these things. The problem is we're like at the end of our grant, and so I don't have a lot of any money to be paying people to like updating our code base to check things. Because yeah, you're right. We could be saving time.
Yeah,
or
you can also just add like there's easy ways to convert rich text to plain text. So it feels like for common case problems you're running into, there may be ways that you can streamline the workflow pretty well just with a way to or just by finding like some easy checks.
Yeah, definitely.
So just say one of the things about the open access versus not, and we run into this with things that people seem to all other services. One thing is whatever you tell them is the license, that is the license, and they can either use your tool or not. Typically we have given an option to keep things confidential or not, and it's up to the user.
Right.
But I think that having these things open in general is probably a good idea unless there are somewhere incomplete. Because I can understand the concern is if there's a proprietary sequence coming into your service, well, on some level, maybe you could understand people keeping it secret. The other problem you get yourself into, though, is if you're giving them an expectation of privacy, then if there is a data breach, you do have a problem. Right? Whereas if you just say everything's public,
yeah, that's true.
You're actually exposing yourself to some potential liability.
Right.
If you're giving people the idea that these things are secret.
Right. Yeah. Yeah. So the good thing is we have like a terms of service that at least like deals with a lot of that. But yeah, you're right. The open part is good. I guess for you guys, how public is it and how do you share the results? Like, could someone download all the results from you guys easily?
So someone could spider all of the public results. When a user submits a job, they have a choice of either making it accessible only with their username and password or not requiring username and password. So a lot of the results are public, but not all of them. I have to look at the statistics.
Sure.
Most recent, I think it's about 50-50. Some people who don't care, like you don't have to set up an account in our system. You just want to make a publicly available result. So you just get a link later, and then anyone can go to that link and they can get the data.
Okay.
So it is totally up to the user for most of the services right now. But it could be pushed in either direction. But yeah, I think how close are you to the end of your access time?
We keep going over. Our problem is like our user base keeps growing and we keep getting it and then we have to get it. We're applying for the next level up, like maximize. Is that what you guys have? Yeah. Yeah, I think we keep getting it and then we keep running out of time and then iterating on that. Yeah, I mean, I think the question that I can't figure out is like whether I should right now people can choose all the tools, and everybody's like, I know I should run AlphaFold, and that takes the longest to run because the sequence alignment step, and I almost want to just be like, only after you run collab fold, or like start off with collab fold, please. But people get, I think, confused by names of.
Well, so one of the other problems we're trying to run into is, Xfinities is a horrible architecture for running multiple sequence alignments. We actually run those locally and then split the lower expanse to run GPU jobs.
I see.
So you might want to look at other places like maybe Rockfish or the new one, the new one at Purdue, like Andro 2 or something like that.
I see.
Systems that are better suited for this kind of things.
Yeah.
The gateway allocations can go to those as well.
Yeah.
So you might be able to do a lot better.
It'd be pretty easy to like move those text files around. Yeah.
Yeah. And then
that's a good idea.
Consider as people think of the field, for especially keeping things anonymous, is not the kind of money, but grant information. Because the thing that we really need better than anything else with access is being able to point to the NSF and NIH grants that you are supporting. So that more than anything else is probably what we need to be collecting politically if you want to make this sustainable.
Right. So maybe like you get some free amount, and then to get more time, you give us
straight affiliation with a federal grant.
Yeah. That's a really good idea. Do you guys do that?
So we don't, but I think that has not been an issue. But like when I was in grad school, I was working on BMD and Mandy, and there we forced people to give all their funding information when they were registering for it because we had to collect this resource.
Yeah, that's a really good idea. Thanks.
Future idea about dividend window. At the beginning, you said you want it to be for people.
Right.
There are so many those people out there who will just do that and not even want to go and buy course.
Yeah.
I think that might just contradict.
For sure. Yeah. I guess I definitely was just thinking about the collab fold notebook that's become really popular. People are used to like these clicking to play button down Jupyter Notebook and like changing some knobs. The nice thing is that's also interactive, and you can have really nice graphics displays too. Where it's much kind of trickier to do that in the web stuff. We could do it, but yeah.
If you, I would say a virtual machine here, we've actually been talking to kids about this recently. If the concern is that you can't synchronize the queue time for like the Jupyter Notebook or whatever interface you want with what Xfinity is doing, you could do it asynchronously with Xfinity to still have an active user experience on like a server, either physical or virtual here, that you have complete control of. And that would be a really nice user experience.
Right. It runs and it tells them, go here, your job's finished, go here and like interact. Yeah.
As I've seen this, that can worry in a good way because it's an opportunity, because educating users how to interpret this information is actually really hard. So if you're going to have a user to, a wizard to run it, you want to see the wizard to analyze it too, and have like giant warning signs about low confidence regions of the structure.
Yeah, exactly.
Or like if their MSM is really shallow, be like, I don't want to trust this. So
yeah,
those are, I think,
that's a good idea.
As part of the shell you put around.
Yeah, that's a good idea.
So for the structure information, sometimes people can like model in terms of the
I mean, I think there is a model. There's like one automatic model building software that we support, which is using this new program called Model Angelo. People will use it in a workshop. People do put like bad maps in, but that program at least fails in like a crazy way where like the bad map will add like 5,000 chains into a model, and then it like crashes the job. It becomes a mess, but at least it crashes and like it didn't work. Because you're thinking about like someone trying to take a bad map, model into it, kind of run away with like a bad result, sort of.
Yeah, or there's a lot of interaction between experiment and model.
Yeah, I mean, I think we could do more. It feels like most of these are just structure prediction, not really. I think there's these weird camps where like if you're doing AlphaFold, you need either collab fold or this or something. But if you're doing cryo-EM, it's like you are somewhere in between, and maybe you have local stuff, and then you do some things on COSMIC2. So it's kind of a weird landscape. I think it's fragmented. Great, thank you.
we're having computer issues, so we're almost there on the other one. Oh my goodness.
Anyone have a different HDMI to USB-C? Normally I use it, but like I said, everything has been going. Thank you.
And then can you sign into the Zoom too when it gets back up?
Yes.
Would you email it to me or to my person?
Yeah, I can probably just airdrop it on someone's. I'll do it on yours.
Sure. It's called, things on MVP. Yeah.
This is something, you know.
Yeah, that screen's you guys your best.
Okay. You on Zoom or I guess I should get.
Yeah.
I'm from a computational chemistry lab. It is not the case that I don't know how computers work. That is really bad at 3:30 p.m. today.
Oh, I sorry, that's me now.
Recording in progress.
Okay.
Okay. Looks good. And then I guess I'll just have to share my screen.
Oh yeah, share screen.
Is this the screen you see on Zoom? Okay. Finally. All right. 8 minutes late. I really have to, scoot through some of these introductions. I'm the presenting author. I go by Argo. I'm a postdoc in Charlie Brooks's group. I guess after 4 years, that's where I am. This work that I'm going to present today is the work I've been doing for the last couple of years with a bunch of other folks in the group, Azam, Luis, and Tan. And this work took many phases as it started and where it is at this point. But the common message, which is what I'm going to share with all of you today, is what we have found out about where the two very popularly used general force fields, as in force fields that are general enough that you could use it on any arbitrarily small molecule. What are the limits of these force fields? Okay. More specifically, I'll be focusing on what are the common limits, and then what are the differential limits, and then I'll try to explain, demonstrate why we think that these are the limits, what physics underlies the kinds of limits we see. And all of this is going to be done to the prediction of small molecule solvation free energy. So what I'm going to talk at large today is, well, enough about the trajectory of the project, but then I'm going to go and talk about how CGenFF and GAFF, CGenFF being CHARMM force fields extension and GAFF being amber force fields extension to small molecules, how they perform very similarly in terms of predicting small molecule absolute hydration free energy. Okay, so on an aggregate level, they look like they have very similar performances, they're very similarly accurate. But then using a machine learning and SHapely additive framework analysis, I tried to link certain errors in both of these force fields to specific molecular compositions of the different compounds we try a protocol on. And then I try to explain what those common areas of chemical space are where both of these force fields have problems, what are the different areas, and then I link specifically that charges are responsible for some kind of error, in that it's responsible for oversolubilization in our prediction, and that hydrogen's radii could be responsible for the other kind of error, which is undersolubilization. So the protocol we chose was this very basic, basic because I guess we have been using it for some time, but I'm assuming many of you are familiar with the use of alchemical free energy methods, where you compute the, on the left, I show a thermodynamic cycle for computing the absolute binding free energy of a given ligand to a certain receptor. And in this, which is what is of more pharmaceutical relevance to a company that's, intends to design drugs. But there's this leg here, which encapsulates the solvation part, as in how does a molecule, or what is the balance between a molecule's affinity to stay in solvent versus being bound to a receptor. So it's the affinity for solvent is what its absolute solvation free energy is. And alchemically, how one does that, I mean, this exact process, how one tries, how one computationally gets the free energy out of it, is they perform this kind of alchemical transformation where in the solvent or in the aqueous phase, they decouple the interaction of a small molecule with its environment. And they do the same thing in vacuum and then construct a thermodynamic cycle, which could look like this or could look like this. But eventually you get all of these different free energy terms, put them, add them up appropriately, and then get the final free energy, which is the HFE, hydration free energy. The protocol that we worked with is something that we implemented in the CHARMM program, which is what we commonly use in the Brooks group. And we integrated CHARMM through its new Python interface called PyCharm with this multi-state Bennett acceptance ratio or MBAR technique, which is equivalent to FEP or TI, or it's in the same category as FEP, free energy perturbation, or TI, thermodynamic integration. And using CHARMM simulation and MBAR calculations, we were able to obtain the free energy. So I'm not going to go through all the different steps of optimizing this protocol, and I'm going to jump right into the results that we got from applying this protocol on a total of 642 molecules from so-called FreeSolve database. It's a database curated by David Mobley's group at UC Irvine. Of these 642 small molecules, we were able to successfully apply this protocol on 614 of them. On the ones that we could not apply were because CGenFF could not parameterize them. In some of them, our protocol just failed because of convergence issues. And there were 10 other guys. There were significantly large errors, which I'm totally putting out of our analysis. Conveniently, because these 10 molecules just happen to be pesticides and insecticides kind of thing. So they were not medicinally relevant for the sake of our conversation. So what I show you here in this plot is how the prediction of 614 molecules, their absolute hydration free energy on the y-axis compares with their experimental hydration free energy, which is on the x-axis. And you can see that the mean absolute error is 1.06 kcal per mole, and the RMS error is 1.66. Yes. I will get to that. Now, these are the numbers from using CGenFF, and these are the numbers from using GAFF. Now, we didn't particularly apply our protocol on all of the compounds with GAFF parameters. free-salt database provides you these numbers. They provide the experimental numbers and the numbers they predicted using GAFF force field. So when we compare our MAE of 1.06, which is very close to their MAE of 1.06, and very close to their RMSE of 1.42 versus ours 1.66, we see that on an aggregate sense, both CGenFF and GAFF have very similar performance. Okay? But when we look more closely into the data and ask the following question, well, do they also give you the same kind of errors across all the molecules? Or if there is a specific systematic bias for one kind of molecule over the other? What we see is that the errors are not as correlated across the two force fields as much as the predictions might be. Okay, so errors have a Spearman correlation of just 0.36, and it just tells us that at an individual molecule level, the two force fields differ significantly. Okay, so when we just plot the distribution of error from the two force fields, so blue is CGenFF and yellow is GAFF. Well, there is one way of just looking at it, but some of the key numbers that you should just focus on is the following. Of the 614, 103 or 17% were oversolubilized. In that, by a definition of the term, around 103 of them had an error of less than -1 kcal per mole, as in they had a larger negative error. Okay, so our predictions say that they like being in water much more than the experiments would suggest. In terms of GAFF, only 67 or almost half of them had that kind of behavior. On the other hand, there were 120 of the molecules in CGenFF that were undersolubilized, as in the error was more positive. In GAFF, this went up to 218. So this tells us that there is a tendency of GAFF to somehow undersolubilize molecules. And CGenFF has a relatively reverse sense of solubilizing molecules, in that it causes more of an oversolubilization than undersolubilization compared to GAFF. So then the task that we took up was trying to understand what about a certain molecule would make it oversolubilized or undersolubilized based on the force field that you were using. Go ahead.
How do you choose the threshold of form?
Arbitrarily, but we justified its use because it was around the MAE value, and therefore these were outside of the one standard deviation, if you may. So this is a busy slide, but I think most of the explanation will be using hand gestures, okay? So what we did was we took every single molecule and represented it vectorially in 3 different ways based on its functional group composition, okay? I'm going to only talk about the way of the 3 that we chose to then work with, which was using max keys, okay? So max keys are a set of 166 keys of chemical fragments, and you get a representation of a molecule based on if that key is present, how many copies of that key is present. So for example, CO group or oxygen double bonded to something, that kind of thing, okay? And so you get this vectorial representation of every single molecule, and we fed it through a gradient boosted tree to reproduce the error in the solvation free energy, not the solvation free energy itself, but the error, in order to understand what key might have been responsible for the error that we see. Now, to understand or to find out what key was responsible for it, that's where we bring in what's known as the SHapely analysis. SHapely analysis or SHapely Additive framework, also aka SHapely Additive framework, what it tries to do, it's part of this tool set called explainable AI, where they try to explain why a machine learning architecture gave you the kind of result you got. And SHapely analysis just assigns every single element of a vector some kind of feature importance value, or aka SHAP value, all right? And that SHAP value, when you add them together, should give you the value you were trying to predict, in this case, the error, okay? So if a molecule had a negative error, I would be interested in those fragments that had a negative Shapley value, because they likely contributed to that negative error. Reversibly, if it had a positive Shapley value, it likely contributed to a positive error, okay? So using that definition of Shapley value and that understanding of it, we then sorted all the keys, max keys, based on their mean Shapley value. When we just focused on the oversolubilized molecules, we focused on the mean negative Shapley value because they were most likely to be responsible for oversolubilization. And what you see here is a sorting of the top 10 max keys out of the 166 minus 36. And I'm going to skip the detail. But you see the top 10 keys with the largest mean negative Shapley value, which we, by our definition, would be most likely to contribute to oversolubilization. And these Shapley values have the following smart key representation. Now that's important because smart keys are loaded with wildcards, okay? And when you have a wildcard, it only gives you part of the information, or it gives you a general information. For example, key number 136 is oxygen double bonded to some atom. Now the question is, well, it's oversoluble when it's double bonded to any atom, or is it oversoluble when it's double bonded to carbon specifically, or sulfur or phosphorus, something like that. So then the next effort was trying to map each of these fragments to unique, very specific fragments, and then counting which ones of them were most likely to appear in this oversolubilized set of molecules. Okay, so this is just for CGenFF oversolubilization, but this is CGenFF oversolubilization, same thing for GAFF. CGenFF undersolubilization, same thing for GAFF. Okay, so we analyze each of these 4 sets separately. And this is what we found. The top 10 keys that we had, when we mapped them out to specific chemical fragments, they mapped into, obviously more than 10, but different numbers, okay, of fragments that were linked with oversolubilization or undersolubilization. Of whatever number you got out of those, we took the top 25 based on the population or their frequency of presence in the data set. And that's what I have here for CGenFF, and I have here for GAFF. And on the x-axis is the error of the molecules that have these fragments. And how each of these fragments are represented, we came up with this expression called Sybil atom type molecular strings, or SAMs, which at least legibly tells me what kind of element. So C2O2 tells me it's sp2 carbon bonded to an sp2 oxygen, okay? And then NPL3O2 is a trigonal planar nitrogen bonded to an sp2 oxygen. So all of these fragments seem to be linked with oversolubilization. Like I said, CGenFF and GAFF. Now, there are some of them that are common. So you see C2O2 and C2O2 in both these cases, okay? And then there is FC3FF. So this is trimethyl fluoride, which is also present in this set here. What you won't see, so this is just a pictorial depiction of the fragments that were common in both of these cases. But what you don't see, and which you will see in the next slide, is that NPL3O2 is not present in this set. Not that I want you to look and find it, it's not there, but I'm just telling you, okay? And it's going to be important because when I now look at the undersolubilized fragments, you're looking at this with the same lens, but now using the positive mean Shapley values, I see that in the GAFF side of things, I do see an NPL3O2, okay? So this fragment, NPL3O2, which turns out is from the nitro-group, has an oversolubilizing tendency in CGenFF, but an undersolubilizing tendency in GAFF. On the other hand, you see that O3, which is sp3 oxygen, is undersolubilizing regardless of the force field you use. And largely all of these O3s that were undersolubilizing came from the hydroxy group, okay? And then there is NPL3, and then there is N3, and these are just amine groups or some kind of amine derivative, okay? So with all of these 25, 25, 25, 25, 100 of these fragments, yes, go ahead.
Oh, sorry.
No, that's okay.
So input is these vectors and are they on the same slide?
Yes.
And I haven't done Shapley yet, but my understanding is that that it gives you the positive Shapley, this is contributing more to the reason for the variance rather than like this negative positive dominant Shapley. That is what I was really confused.
Now this work was done by Azam, but based on my understanding of SHAP, each of these feature importance value, aka SHAP values, must add up to give you the Y, the predicted Y value, which in this case was the machine learning architecture's prediction was the error. So the positive or negative was the contribution with, there was no, it wasn't interpreted in the sense that if it was positive, it had a larger contribution than the negative one. It just, they all had to add up to give you the predicted Y value, the Y being error in this case.
And these are trees?
Yes, we used gradient boosted trees, yes. Okay, so of the 100, well, non-unique set of fragments that we had, sorry, go ahead.
I just heard, since we were
Yeah, sure.
I just for predicting the error, how accurate was the actual network, and do you know if when using SHapely for scalable AI, does having a highly accurate predictor mean more meaningful SHap values?
So the answer to this question would largely lie with Azam because he's the one who did all the ML, but I'll tell you this. The way we found out that the LGBM booster, LGBM, whatever, gradient boosted tree would work the best is based on his use of this AutoML package, where a bunch of different neural networks get tried on the same set of data, vectorial representation and Y values. And then based on them, you find out the best one. And then after finding out the best one, he tuned the hyperparameters for this one, did tenfold cross-validation and all of that stuff, and then eventually found out that, this was the best way to go with what we have. And then we derived the SHap values based on the best parameters that gave us the best reproduction of the error.
Okay.
So that's how we landed on that. Okay. So now in pure English, that would, all of that fragments would just boil down to this 6 main fragments, which have something interesting to tell us about CGenFF and GAFF. We found out that all the carboxylic acid groups, okay, they generally tended to be oversolubilized than they were undersolubilized, so more negative error. And the fact that you see more yellow on this side, which corresponds to GAFF, tells us that carboxylic acids are typically more oversolubilized because of the GAFF parameters. Okay. The same, well, you could use the same lens to look at trimethyl fluorides, and we see that CGenFF has a tendency to oversolubilize trimethyl fluorides. On the other hand, when you look at hydroxyls, which are undersolubilized by both of them, CGenFF and GAFF, they relatively have the same way of undersolubilizing, except GAFF does it slightly more than CGenFF does. Okay. It becomes interesting from here on out, as in more interesting from here on out. When you look at aliphatic amines, then CGenFF has systematically much larger error than GAFF, and in the same direction, albeit, but CGenFF trends to undersolubilize amine compounds much more than GAFF does. Okay? And nitro-group, on the other hand, is undersolubilized or has a lesser error because of GAFF versus more negative error because of CGenFF. And then there are trimethyl fluorides, which is also oversolubilized by CGenFF, not so much by GAFF, but I'm going to skip the rationale behind this one. I think it has to do with lone pairs on the chlorides. So now, one of the things that I was interested in is trying to understand what was making this nitro-group behavior very different between CGenFF and GAFF. One of the things that we looked at, or we finally found out, was if I take one of these nitro-group compounds and I just find out the potential on its solvent-accessible surface using CGenFF parameter and also obtained using GAFF, and if I compare the two, this is what I find for this particular compound, which is a trimethyl nitrochloride. Okay, and what I want you to appreciate is, so the potentials because of GAFF are on the x-axis, and for the CGenFF is on the y-axis, and this is the x equals y line. You can see how it's strongly polarized because of CGenFF, as in it goes all the way from -20 to +50 because of CGenFF parameters versus -5 to +5 because of GAFF. Okay, and those points that are highlighted in red are spatially closer to the nitro group in space. So around the nitro group, there is a strong negative potential because of CGenFF partial charges, which probably is hanging on to the water hydrogen atoms and just keeping the water there. That's probably why it's oversolubilizing. In fact, we see this trend across a whole bunch of other nitro compound, nitro molecules, including, just nitro, what is it, nitroethane, ethyl nitro, something. Okay, I just can't do the time names, right? And I'm not showing you the other data, but there were 14 of these, and all of these similar had this kind of behavior where the potential around the nitro group was much more negative because of CGenFF than because of air. Now, when we look at the charges of the nitro group, which is probably, which is the reason for this kind of potential, and compare the value that we get from GAFF versus CGenFF, we see that all the oxygens are more or less the same. Charges on the oxygens are more or less the same. It's the charges on nitrogen that varies so much so that when you take the total charge of the N with the two oxygens on it, you get a much negative charge because of CGenFF than you get because of GAFF. That probably explains why there's a negative potential field around CGenFF, around the nitro group because of CGenFF. On the other hand, I mean, we could use the same argument to also explain why carboxylic acids are more oversolubilized by GAFF than by CGenFF. And I'm not going to go into those details, but the argument holds, is the point. However, when we looked at amine compounds, which were undersolubilized by both CGenFF and GAFF, we could not really use this potential-based argument to say why they were undersolubilized. Even though I'm not showing you the data here, what we did find out was around the amine groups, the potential was still negative because of both of these force fields, where I would use the same argument that they held to the water oxygen tightly, but they're undersolubilized. So something else was at play besides the charges. So then we looked at the van der Waals radii, okay, of the atoms that make up these amine groups and also the hydroxyl groups, and found out the following: that whereas GAFF tends to have the same radius for any kind of amine hydrogen, according to CGenFF's description, there are two kinds of hydrogen you can have on a nitrogen from an amine. One that corresponds purely to a hydrazine, and I just believe in it is hydrazine, and the rest of them are put together, like they group up there, and these are all the amine hydrogens, and they're larger in CGenFF compared to GAFF. The effect of that is shown in this figure, where we took a single water molecule around an amine group and just measured the Lennard-Jones potential of interaction. And what we find out is because of CGenFF's parameter, there is this kind of larger variant, which is probably arising from the larger radius of hydrogen compared to GAFF, which also tends to have a bend. So that does tell us, this gives us some sign that this hydrogen has a tendency to dispel this water, which is why CGenFF amine compounds are systematically more undersoluble than. However, these hydrogens are really small in comparison to the nitrogen or the heavy atom it's bonded to. So then the question comes, is it really that big of a difference? Just changing the hydrogen's radii that much? What we did therefore was, we took all the amine-containing compounds and just changed their hydrogen's radius from CGenFF to GAFF values, and then computed the new free energy with this hybrid force field. And in blue is the error from the original CGenFF, in green is the error from original GAFF, and in orange is the error with this hybrid force field. And you see, just by changing the radius of the hydrogen, shrinking it by actually just 0.3 angstroms as an Rn/2, you get a drop in the error, which therefore supports our hypothesis that bulkier hydrogen was responsible for this kind of undersolubilization. And at this point, I wish she was here because she asked this question about the penalty score. So when you run CGenFF, it gives you a penalty score about its confidence in the parameters. And the question was, well, would it also tell us how good its solvation free energy would be? Turns out that the correlation between the error and the penalty score is just very poor. Okay, there are some molecules with very large penalty score which have very low errors, and molecules with very low penalty score which have very large errors. So penalty scores are not a good way to foretell if your predictions are going to be accurate. I'm going to skip this part. This is just a comparison with another protocol which gave us the same results. And I'm going to jump into one of the final slides, well, penultimate slide, just commenting on why this charge difference could be an important thing for force field developers to look at. One of the things that we found out, and I also talked in the beginning, was CGenFF had a tendency to oversolubilize more than GAFF. Okay, and that is somehow also reflected in the fact that in a lot of these 614 molecules, the dipole moment difference, as in CGenFF minus GAFF, was largely positive. As in most of these molecules, the dipole moment because of CGenFF was much larger. Therefore, telling us that CGenFF tends to describe molecules as if they were more polar. Okay? So it's not surprising that for those molecules with very large dipole moment difference, they also differed significantly in the predictions of the solvation free energy. Okay, so larger the dipole moment, the more favorable the molecule was in water, which makes sense. But we wanted to understand why was this happening? Why was this systematic bias towards having larger dipole moment? We believe it has to do with how CGenFF and GAFF parameterize their molecules and how they get their empirical training set to begin with. And without going into much detail of what terms they use, I'll just say the following. CGenFF tends to do does the following. It takes a water molecule and it places individual water molecules separately at each of the hydrogen bonding site and runs a QM at Hartree-Fock level of theory, gets an interaction energy, and from there determines the charge on an atom that would best describe that quantum mechanical interaction. Okay. GAFF, on the other hand, it takes an entire molecule and uses Hartree-Fock 631G level of theory and computes its electrostatic surface potential around the molecule in gas phase, and then tries to determine collectively the charges on the atoms that would best reproduce that electrostatic surface potential. So there is a local perturbation effect in CGenFF, and that's missing in GAFF. GAFF has a more global way of approaching the problem than CGenFF. Because of this local perturbations, it's very likely that electron densities get shifted around, and therefore the charge separation on a bond are much more skewed in CGenFF than it is in GAFF. And that is what this data is showing, and I won't go into much detail about it. We see signs for this, and that is why we believe that CGenFF tends to largely skew bond dipole moments, which probably results into a larger dipole moment overall. So in summary, nitro-groups and amines are the most interesting. Nitro-groups were oversolubilized by CGenFF, undersolubilized by GAFF, and we believe charges were responsible. And amine groups were undersolubilized by both of them, just much more so by CGenFF, and we believe the bulkier hydrogen atom was responsible for that. And then, the rest of it I just went over. So I'd like to thank every single person in this group who helped us do this work, and I'd also like to thank Stefan and Johannes from University of Vienna, whose data I skipped, but they helped us, make sure that there was nothing wrong with our protocol before we started blaming the force fields. And then Alex McAdam, the guy who is now taking over the development, who has been taking over the development of CGenFF, we had some good conversations with him. And then David, group wizard, and everyone in the Brooks. And thank you, Mike, also for the laptop. So since we believe it comes from the charges, it makes it more difficult than just tweaking the van der Waals radii, because you will want to preserve the net charge of the molecule. So if you just reduce the charge from CGenFF to GAFF in one section, you would have to compensate for that in a different section. And then you just might be totally messing up the charge distribution. So therefore, I believe it's more difficult than just dealing with van der Waals radii. Well, in that case, you're running into a oxymoron, right? You cannot generalize if you are worrying about the type of molecule. So that is the new push. They are going anti-general now, as in for every single congeneric set of ligands, they're coming up with their own set of force fields.
Yes, maybe one other question is, could you average in like what the difference between the two?
You could, or you could just go with OPLS's approach or CM1A charge model, which has been found out to be a good hybrid ground between the two. So maybe that might be a more physically intuitive approach, because how would you justify averaging just by saying, oh, and why did you choose the two, that kind of thing? Yeah.
So does the max 166 like include functional groups that maybe like molecules have functional groups that are not active max, or is that possible?
Now, I can see how that might be possible, which is also very unlikely to happen because they say it's extensive and I've seen that it is extensive. But I did check and I saw that every single molecule had at least one, not all the vectors were zero of the 166 keys. There was no such molecule with everything zero. So every molecule had some representation if they found something in the max keys. It is possible that max keys did miss something.
Right. So like, what if like max key does not accurately describe the molecule?
Yes, that is a limitation then. Yep. I can stop sharing.